something down with an imaging system. So usually it would look something like this. Again, you'll have to excuse the slightly non-straight lines. I don't know why I'm imaging Stickman today. That just seems to be what I'm doing. So here I've shrunk down an image. Yeah?
Yep.
But what you'll notice is that the rays in this system, here they're really, really narrow. And here, the angle range is much wider. It turns out basically that even if you're not concerned about imaging, even if you say, okay, I don't care anymore about where the light came from, you still can't concentrate light any more efficiently than this. So if you put a diffuser in there, what happens is it doesn't concentrate the light anymore. In fact, it probably spreads the light out. It's just that you've lost the position information from that light. And so you will get light from the whole image through the slit, but you'll get not very much of it through the slit.
Right. Yeah. The goal of the diffuser is actually just on the back end of the diffuser for that surface, at any point at that surface, to see equal intensity. So without doubt, you lose a lot of light. But
yeah,
regardless of the location of the source of the light, it will have the same impact on on anywhere on the back of the diffuser. Right. That was the goal, or that was the intention. So I totally agree. You're going to lose a ton of light, which we probably can't afford. I guess that's open question, but
yeah. So I mean, I suspect using a lens and a diffuser probably helps, because if the lens even reduces the size of the image by a factor of 3, then you win by a factor of 9 in intensity. Because of course it all goes as the square of magnification. So it's almost certainly worth including a demagnification lens. But do you not get why you need 2 lenses?
Yeah, I do. Yeah, okay. So the trick that I'm like, so I just think about it like a cost and manufacturability perspective. So
yeah,
the reason that I'm trying to get rid of things, well, obviously that's just like a cost perspective, but from a manufacturability perspective, it's hard to make a very small. We have a lot of requirements. We have, let's say, we're assuming, just picking numbers out of the air, we're assuming we're going to need 2,000 images. That those 2,000 images will have to be unique and as random as possible. We can't make them perfectly random, at least not with the current design. And if we're going to do that, it means we need lots of little. We're going to need an object with lots of holes in it. And for me to manufacture that object, if it's 1 centimeter in diameter, that's going to be much harder to do than if it's 5 centimeters in diameter. You know what I mean? So I'm trying to figure out, like, how can we keep that mask as, not so big where we're building like a desktop unit, though we will initially, but not so small where it's not manufacturable. So like what combination of objects allows us to do that?
Yeah, I mean, I guess the important quantity there is the size of the mask and the number of pixels in the mask.
Correct.
So most of the single pixel imaging literature, you're talking about images that are between 10 and 100 pixels across. So these are not super high resolution images.
Right.
Because basically the more pixels you have, the more images you need to do a reconstruction. So let's say the size of a pixel is, I don't know, a 50th of the size of the image. What's the smallest hole you can make with the laser cutter? I don't know, 0.5 millimeter?
No, that would be I could test. This is all testable. I mean, I'm actually ready to
Yeah,
do that. So I've got the laser cutter. I'm ready to go. That's kind of why I started sketching those out. Because this Friday I might go
yeah,
in and just make some things and maybe take some pictures so everyone can see.
yeah.
But my guess is, well, there's a couple of factors too. If we're going to do this gear type, there's a minimum thickness required to make the gear function. Like we can't make it paper thin because gear's not going to work
Yeah,
paper thin. I think a 16th of an inch, which is like 2 millimeters, is probably doable if we have a robust structure connecting the gears. Like all that kind of stuff. I think it's probably doable. Eighth of an inch, certainly. 16th is probably doable. That's pretty thin.
Do you do you think there's any mileage in doing something like making the disc out of a piece of clear acrylic? Sorry, making the gear out of a piece of clear acrylic, or the rotating disc, and then just sticking a really thin mask layer of aluminium foil or paper or something on top of it.
Could, yeah. Do I think that will necessarily? I think if we were doing, okay, I guess here's my uh, opinion based on intuition. If we're doing a 16th of an inch thick, I think we may as well just do it all directly in the acrylic because I think we'll get the resolution we'll get sufficient resolution from the laser cutter down to probably a millimeter. Um, I think if we have to use an eighth inch, then you're probably right because you've got at an eighth of an inch you have some angling, of because it doesn't cut perfectly straight. There's always a little bit of
Yeah,
angle on the cut, and then also just by nature of the fact that it's thick, um, and it's always going to be at an angle, that's going to affect the results. So, uh, uh, from a manufacturability perspective, the ideal would be is if we can do 16th of an inch and do it all directly on there.
yeah,
That's my preference as a first try. If that doesn't work, you're right. I think there's other options.
yeah. I mean, so what I started thinking about on my way home from Gosh um, was I think what I would do, and what I was thinking about is actually quite a different beast to what you're suggesting, and it will have some advantages and some disadvantages. I was thinking it would be interesting to make the spinning disc out of something like chrome-plated glass, which you can order and have someone pattern it with ridiculously high resolution. Um, Now that's not going to be super cheap. Um, Probably you'd be talking about 50 to £100 for a disc, um, but you could have a ridiculous information content on that disc.
Right.
Um, so, and then I sort of let myself run with that flight of fancy. So I meant to draw this up beautifully in Inkscape and never got round to it, but I will doodle it here. Essentially, the system I think will be really fun to play with. And this is more because I think it would be an interesting single pixel system to do the maths for and so on. So you'd have two disks. Let's draw some little motors in there to spin them.
Yeah. I like this. This is sort of the
Um,
initial concept was two opposite spinning discs, but I didn't quite know the details enough to figure out how it would work from a math perspective.
yeah, so you've got, as before, you've got your lens forming an image on the disk. Uh, then you'd be sort of re-imaging that onto your big fat sensor. Um, and at this point, I was just assuming we could use like a nice large area photodiode. Um, and then these two discs could be patterned differently. And what I was thinking was you could take your disc. So the middle bit will be taken up by the motor. Then you put some crazy pattern around here. And then on the outside, you essentially make a little encoder. And then put 3 photo interrupters, so just like little photo transistors, LEDs, around the edges of the disk.
Do you have to have electrical connections to them?
Yes. Sorry, these are not mounted on the disk. They're mounted on
sitting
the
behind them. Okay, I see what you're saying.
yeah.
Gotcha.
So you have like the photo interrupter looks like that, then your disk fits in between them. And so if you then collect the signals from those 3, you get something that will, I guess it will look kind of like that. And by looking at the timing of those, you can work out not only the speed of the disk, but if you do the encoder right, then you can get the angular position of the disk plus its x and y shift. Does that make sense? So from those timing so what I was thinking is, don't bother with a stepper motor and doing all the open loop positioning. Instead, use just a really cheap DC motor, and just track where the disk is. Then essentially you need your sensor to be really fast at this point. So this would almost certainly be useless with the spectrometer. But if you do this for both disks, then of course your mask is the product of the 2 disks at that particular position. And I think you would need to do some maths to work this out, to show it's actually a good idea. But if you pattern the disks right, you could do some quite cool stuff by spinning them at different rates.
Yep.
And so you could, for example, you could have one disk with a really coarse pattern on it and one disk with a really fine pattern on it. And that should then allow you to reconstruct relatively fast, low-resolution images, but then go back and post-process to fill in the high-resolution information. So some of the really cool video ghost imaging stuff does this, or single-pixel imaging, where, essentially you're doing a low-resolution video thing that you can use for a real-time preview, but you're also recording enough information to go back and reconstruct the same video at much higher frame rate. Much higher resolution.
How hard is that? Well, I guess my question is, how hard is that math and design? I mean, is that a huge effort, or is it like you can throw up a design and figure out the math from that relatively easily?
I think designing the hardware is relatively easy.
Mm-hmm.
The stuff that basically spins the disk and knows where the disk is and records. So essentially what you need to record from the whole system, you need to record the position and angle of both disks. And then also the intensity as a function of time. And so if you wire the photo interrupters and the detector into a relatively fast data acquisition device, which might or might not be an Arduino with some kind of ADC plugged into it, That part I think is relatively doable. The maths to reconstruct it, like I could write the easy version of the maths to reconstruct it quite quickly, but the really interesting stuff comes when you throw like hardcore compressed sensing maths at it.
But there's like a kind of a minimum viable product that we could try to hit that wouldn't take 2 years worth of research. Yes
Yes,
or no?
I think that would be a safe statement. Um, I mean, the reason I haven't pushed this harder is that, I mean, if what you're interested in is hyperspectral imaging with a Hamamatsu mini spectrometer, I don't think this is the right system.
So, well,
Because
Did you see the new? There was a post. So I think we've got the full. Well, there's a couple options. So we can the there was a group out of MIT that was working with somebody at Target, and they were interested in making a device using the mini spec to do product identification, which is like what everyone's doing. Everyone's like, oh, I can tell a Macintosh apple from a Gala apple, or whatever, using spectrometry. Anyway, so there's this whole and then you just see this repeated in field after field after field. So
yeah,
so anyway, they were working on that. And so he took the group gets the firmware that was provided by group gets, which is the same firmware that we took and integrated into the into the Coral spec at PhotoSync. And I asked him like, hey, how much faster could we get this basically? Because he had put some effort into it and could do some of the lower level programming. So anyway, he took a weekend and kind of knocked it out, and he got it down to 600 microseconds for all 288 channels. Now that's at minimum integration time. But I also know, based on my discussions with Chris, that minimum integration time, even in a fluorescent lit room, we're still getting signal. So I think there's always the shift, right, of like, well, how much do you lose versus how much do you gain? But I think we can safely say that we could do. My guess is, based on that information, we could probably do outdoor lit situations with the type of lenses you're describing. We can't go losing all of our light, but if we're reasonably careful about concentration and light loss, we can probably do outdoor lit situations at 600 microseconds for all 288 channels. And if we were thoughtful, we could probably do a channel at a time much faster than that. In fact, we should be able to do a channel at a time in like a couple microseconds. So if we wanted to try to time each channel individually with each image, your math would be harder, because actually you're kind of like reconstructing each channel's image is actually a separate image, because it would be a separate turn of the wheel. You know what I mean?
Yeah.
So that's a little more complicated.
How does that work with integration time? Is it like a rolling shutter camera? So is it that I'm integrating all the time and I'm just reading out every so often, or is it that maybe it's easier if I doodle it?
No, it's not doing that.
So it's like pixel 1 boom, pixel 2
yes,
boom.
it's that. Yeah, and that boom takes, depending on the ADC that you're using and all that kind of stuff in the resolution, is 2 microseconds to potentially 20 microseconds, depending on the ADC.
And then the integration time is just whatever the integration time is.
Yeah, well, the integration time is, the vast majority of that is the ADC read. So the Teensy has an internal ADC that's 16-bit, but actually it's 13-bit usable, which I believe at the integration. Okay, hang on. There's two. There's two factors. I'm trying to separate it out. The integration time is basically the ADC read time. I mean, it's basically the same. There's some delays where you have to ping the clock to tell the spec to take the read, but that's what he changed. He got that down to like 100 nanoseconds. So basically that's nothing. So it's almost all the ADC read time. That's what you're waiting for.
So this is just the ADC read time, and if you want to do a longer exposure, then I'm just trying to understand how it scales with the amount of light you want to collect.
Right. Yes. So, hang on. So you're right. I'm sorry. There's three pieces. There's there's the fact that you have to communicate with the device, which means you've got the up clock and the down clock of the I squared C to tell it to do the integration time. That has basically been minimized to a microsecond, so that's good. Uh, so
Okay.
that's one. Two, you do have to tell it what you want the integration time to be, and I think the lowest is a couple of microseconds, one or two, and then once it's done with the integration time, it will hold the result, which you can then read with an ADC. Do you see what I'm saying?
Yeah.
So if there's like I think that there's like a sample and hold there internally, which you can then ping with the ADC, and then depending on how long or how the quality of your ADC, that'll determine how effectively you're measuring that held signal. So the integration time at its minimum, that 600 microseconds that I told you for 288 reads, it must be a couple microseconds. And then the ADC read time is another couple microseconds. So, for each one, it's under 5 microseconds per channel, half of that being the integration time of the actual spec, and then half of that being the ADC read time. So the ADC read time will not change. That will always be 2 microseconds or 3 microseconds, assuming that
Yeah.
we don't need to go to 16 bits, which I don't think we're going to need to do. And then
Okay.
the integration time we can adjust up if we choose.
Yeah.
Does that make
Okay.
sense?
Right. I understand.
Okay.
Yeah. So essentially, there's like 2 or 3 microseconds of overhead per pixel plus your integration time.
Correct. That's right.
And you don't get anything for free in terms of exposure. So you couldn't like start exposing all the pixels and then stop exposing them all and then read them all out.
You can't.
You got to do.
No, because it can't. It doesn't have I don't think it doesn't have a sample and hold for 208 channels at the same time, basically.
Yeah.
It's just choosing one at a time. So.
Yeah. Okay.
Yeah. So, but what you could do is if you lined up each channel with a separate turn of the wheel, you potentially that could save you time. So.
Yeah. Yeah. Okay. So. Yeah, that would. And you can presumably also do things like read out only selective channels. So you could initially make an image using just a red, a green, and a blue. And then you can decide based on what you're doing what wavelengths you actually want to measure.
Well, that's an open question. So I would have to go back, or I would have to look into the firmware, or I would have to go back to him to ask that. So my assumption, for sure, I know that if we set the integration time, and we use a timer on the teensy, we could line those two up. But I don't know if, by setting those timers to be the same. Now, if they actually are the same or not, I guess is an open question. You're saying, can you initiate them at the same time? I don't actually know if I have that kind of control over each channel.
Sorry, no, I was meaning if I want to go really fast but I only want one wavelength, can I do that?
Yeah, that's my answer is I don't know. I don't know if you have to
Okay,
run all 288 or not. So that, because the way that they abstracted the code, the way that they abstracted the code, the answer is no. But if you dive down into
I see.
into the library, I don't know. So I'd have to look. If you could, but that's an open question. So yeah, but I can ask. Okay, let me write that down real quick. 'Cause,
Okay, so based on that then actually that's really good because the thing I'm worrying about here is motion blur.
yep.
So I've got my disc. My disc has holes in it. I've got the size of one hole, which is the size of a pixel. I'll call that delta because using Greek letters always makes things more sciencey.
Right.
So one very relevant quantity is how many how many pixels can we take per second?
Right.
And so essentially, the maximum rate at which we can spin the disk. Um, so the maximum speed of the disk is 1 pixel per integration time.
Yep. And the question is a pixel 288 channels or is the pixel 1 channel? Right?
Yeah.
That's
But
basically.
based on what you just said, a pixel is 1 channel. In fact, it's the integration time from 1 channel. So I think it's actually very short.
Yes, it could be very short. I
Um,
believe so, yeah. Yeah.
and so that's like 500,000 pixels per second, which is, let's say, 10,000 images per second, which is pretty much as fast as I've seen anyone do.
Well, another interesting
Largely,
question here. But sorry, go ahead, finish your sentence.
I was just going to say largely because most of the single pixel imaging setups I've seen, they've not had enough light to go any faster than that.
Yeah. Well, there's another interesting point here, which we've seen in our work with reflectances. Oftentimes, people, for most applications, people do not need the full spectra with the resolution that's provided.
Yes.
You can get 95% equivalent predictions from 15 wavelengths as compared to 200 wavelengths. So the other thing that we could do is just skip a whole pile of spectra. Instead of 288 channels, maybe we just use 30 channels.
Yeah. Or I mean, this is where the hardcore maths comes into play. And I'll be fully honest and say I am not the hardcore mathematician that you need. I sort of know what that math is, and if pushed, could probably go and find it in the literature. But I'm not a compressed sensing mathematician. I could probably find people who are, but I think actually yes, you could just restrict the number of spectral channels you use. What you could also do is acquire all 288, but make some assumptions like the image is going to look vaguely similar in two wavelengths that are very close together.
Close. So this is actually exactly what they do with geospatial mapping. They have all these, I've seen it in R packages that make all these assumptions about, spatially similar or spatially adjacent, locations, basically improving the statistical significance based on the stuff next to you. That's basically what you're talking about, right?
Yeah, precisely that.
Yeah.
So the assumption is simply that the data is smooth in lots of dimensions, and this is the core of why single pixel imaging works and is sometimes a good idea. Essentially, it's that if I show you a picture and say how much information is in that picture, the obvious answer is, okay, how many pixels are in that picture? Multiply that by 24 bits for a color image. That's how much information is in the pixel. But then you go and look at the size of your JPEG file from which that image came, and you find out that it's like 1% of that size. And the answer, of course, is that actually the pixels in the image are not all independent. And so compressed sensing, single pixel imaging makes the assumption that not all of the pixels in your image are independent. And so by taking a smaller number of measurements with this mask, you can then reconstruct based on, so the noddy maths, as I might call it, is you construct a big matrix, you invert the matrix, you get the answer. But this only works when you have the same number of masks as you have pixels in your image. However, if you're willing to make those assumptions about smoothness, or to use the word that's more often used, sparsity, So having an image that's smooth is pretty well the same as having an image that's sparse in the Fourier domain, or the wavelet domain, or whatever you want to choose. If you mathematically include that sparsity constraint, you can then solve the matrix inversion problem even in the case that it's massively under-constrained,
Right.
if that makes
No, it
sense.
totally makes sense. You don't need a picture per pixel, basically. It's not just adding and subtracting anymore, which is what
Yeah.
in the case. Yeah.
And so if you were to run the spectrometer with all 288 channels, but you were able to make some assumptions like wavelengths that are very close are going to look quite similar, then probably you can still reconstruct a full resolution image at full spectral resolution, but with far fewer exposures than you might think that you actually would need.
Right. Right. So so I guess there's two questions. So one, if so, part of this experiment in doing all this stuff together is to understand what we as a community can do, and then how we can stimulate other people to contribute to open projects. I know I just stepped into a totally different domain of discussion, but it's relevant.
Oh yeah.
So I recognize here that we have opportunities to build an efficient tool, but that's going to require some specialized skills. So
Yes.
so what can we do to make that the value proposition from us to them most useful? I mean, if we just had the sort of setup and the ability to generate the data, then if we walked up to somebody who could actually do this work, is that valuable enough or convincing enough to them that they would be involved?
I mean, maybe. The easy way to find out would be to go and find someone relevant and ask them.
True, yeah, that's a simple way. Yeah.
I guess if I put myself in their shoes, probably what I want to know is, would anybody be interested in this thing if you do the hardware and I do the maths? So we probably want to demonstrate that there is an interesting application, or indeed many interesting applications. I think if you can show that we can make the hardware and we can bring the application if they bring the maths, I suspect you'd be able to find someone to bring the maths.
Cool. I mean, I think in some ways I had to do that for Hamamatsu because their requirement was that everyone submit why they were interested and what the applications were, because they're in the same boat, right? They're not going to give us free stuff unless they're like, well, how does this increase our sales of specs, which is totally fine. And so each of those people who is getting like a spec submitted as part of that, their application in their own domain. So I think we have that, and then also in having discussions with Hamamatsu, I think, well, there's two things. They're not going to give you free stuff unless they at least kind of think that you're onto something reasonable. And and in detailed discussions with our rep here, there's no usually if you have a bad idea, someone provides you with a smoking gun as to why it's going to fail. And there's no smoking gun from them. They're basically like, yes. Everything you've said makes sense. I think that's probably possible, and there's a wide range of other sensors you can put once you have a basic, mechanical and mathematical device that works. Once you have a teensy and a box and a well-designed gear set and the math to go with it, there's just a giant pile of things you can do. So I feel very comfortable that we can make that case to whoever, to be honest. So, yeah, I think it's doable.
Cool.
Okay, so the question is, we know we're going to have to test this stuff out, and we have a variety of options. What should I send out to everybody? What's the best set of objects that I can send out? so that we can be flexible in testing. Um,
Yeah.
I think maybe we should make that list. Um,
Yeah, I mean, I guess the question is how much of the hardware design do we want to do before sending stuff out to people?
yeah,
Because I guess what we're hoping is that we'll do the hardware design together.
totally.
So it's not like we can nail down the hardware design and then
Yeah,
figure it out. So I mean, obviously the hardware for the stepper motor version versus the spinny, whizzy, fast, don't set the position, just measure the position version is
yep,
quite different. Um, I think the stepper motor version will be much easier to get working because you can get it working painfully slowly and then work on the
yep.
speed. Um, and probably the maths for reconstructing the image is also the same. I mean, give or take the two
Right.
discs thing. Um, so let's not try and get everyone building the super whizzy high speed mask system. I mean, the more people developing it, the better. But I think that's not on the critical path to
Well,
making
what's the
something work.
cost? Let me ask this: what's the cost to that? Like, let's say I'm putting this in a kit. I guess my comparison is always like
Yeah,
low likelihood of return because it's complicated. But if it's also low cost, then I'll chuck it in, right? If it's two regular fast spinning motors and a couple of cheap sensor detector combos, I don't know how much those are. If that's like $10, then we'll
they're
just throw it in, and if it doesn't get used, it doesn't get used. But it gives people a starting point.
yeah. I'm trying to remember. I have bought these things in the past. They're a few pounds each for the sensors, but you'd also need to be able to drive the motor. You probably need to speed
Right.
control the
You need a
motor,
motor driver.
um,
Are those motors? What?
which
They're just voltage controlled. There's no like internal. It's just voltage controlled.
yeah. I mean, I was assuming you just use like the basic cheap little spinny motors.
And what's the current? What's the current draw?
I don't know. I mean, I'm now totally guessing here.
If it's very very low,
But
we can drive it directly from the DAC on the Teensy. Because the Teensy has actually, and actually I got 3.6s, and the 3.6s have two 12-bit DACs on board. Um, so if the current draw on the motors is low, we could drive it directly from the DACs, and those are, that has 4,000. What's 12 bits? I don't know, 2,000 channels. So
yeah, I mean, you might want a transistor because I can't imagine the power draw is that
yeah,
low that you could drive it off a
right. Maybe
microcontroller
once it's
pin.
up and running, but certainly not when
Um,
it's starting.
yeah, um, yeah. I mean, I guess the cost of it needn't be all that much. It depends a little bit whether you'd need three sensors or just one sensor. And of course, there's no reason you'd have to start with two discs. You might as well start with one disc and then add a
Right.
second disc later. That's definitely a
Yep.
stretch goal. Um,
Yep.
but yeah,
The other thing,
yeah, maybe it wouldn't be that expensive. I mean, I think the expensive part is going to
I
be the
agree. I
optics.
know that's why I hate it. I wish we could fix it, but I see what you're saying. There's kind of no like, can't dance around it.
Yeah, I mean, I think fundamentally you need an imaging lens of some sort. And if you want an imaging lens that will form a decent image over a reasonable area, um, like if you go to an optics company and you buy a basic lens, it'll be like 50 quid. Um, I suppose you could try doing it with just uh, a simple singlet lens. So the ones we use in the microscope are molded singlets from Comar, and they are about £10 each once you've added in VAT and transport. Um, that will not produce as nice an image um, as the one I linked, but it's a third of the price, so it might not be a bad place to start.
Well, let's just make a BOM I think that's worth doing. And let's put stuff on there, and we'll see what we can afford. And because I mean, here's what's going to happen, right? We're going to ship this stuff out, people all over the place, and they're going to have different access to different things, which means we're all going to be using different things, which means it's going to be not comparable. Like I'm going to do something, I'm not going to know if it's the same as what you're doing because you bought this from there and I bought that from there, which, variety is good down the road, but I think as a starting point, it's good to have some comparability. So if I make a mistake, I can
Yeah.
see how you fixed it. So I think let's just make a BOM of. You're right that we're engineering this together, but we're I guess we're just putting a flag in the ground and saying like, here's our starting point, a couple options. Let's go from there. I don't think we're wildly off. Maybe we are, but so
Yeah.
if I'll just make a Google Doc. I'll put in the stuff that I've already got. We can kind of cross off things that don't make sense, add things that do. Like you just took my BOM from $17 down to $1.50 with your little geared, you know, servo, which is awesome. I'm sure
Yeah.
there's more of that we could do, and I'll share it and see what people
Yeah.
think, and then that'll be part of the kit, and then I'll just send that out together.
Yeah. The little servo, by the way, I would probably the easiest way to drive that is just with a Darlington pair IC. So you can get like 8 Darlington pairs on a chip for, I don't know, 50p. Because you're not doing microstepping, that is all you need. Um, and actually, depending on who you buy it from on eBay, they might even throw that in on a circuit board for free. And then all you need is just 4 pins from the
Right.
Teensy.
Yeah, we'll have tons of pins because we're not driving that much. Okay. And remember we do have this 2 DACs, so we can control things directly with the DACs as needed. But
Yeah.
cool. Okay, I'll do that. I think we have 2 kind of like reasonable starting strategies. I like the spinning one. I think you're right. In the long term, that's really, really. That's a much. Anytime you can confirm that you are where you say you are with the sensor, you're better off, and it's by virtue of the
Yeah.
fact that you decrease the cost of the motor and you potentially increase the rate of everything, the speed. It's the trade-off might be worth it. But yeah, we won't really know until we fool with things. So
Yeah.
cool. All right. Well, I'll make a BOM and we'll just throw things on it, and I'll try to get them in house before I ship it out. So
Yeah. Cool. Oh, actually, one thing that it might be worth thinking about is if we could include just a regular photodiode.
oh yeah, that's a good idea.
So it wouldn't be wavelength sensitive anymore, but it would be much larger area. And so if we suddenly find there's like a massive signal problem with the spectrometer, it would mean we could play with some aspects of the system without needing the
Totally agree.
spectrometer.
Yeah.
I guess the issue there is how do you convert the photodiode to read a voltage?
Let me.
Maybe I should do some thinking about that.
So we have
I mean-
a circuit. I mean, because we do that in the multi-spec, so I may be able to.
Okay.
Ask Robert. I'll talk to Robert about it. See what he thinks.
Okay, because the only examples of that I've seen have been like super high performance transimpedance amplifiers that cost lots and lots of money.
Yeah, we have a. I'll ask Robert. It might be.
Cool.
It might just be a couple jelly bean parts that we put on a board is sufficient.
Yeah.
We'll have to see. Resolution wise, do you have any first pass guesses in terms of what kind of resolution we need on our single pixel? Like, are we going to need 16 bits or 12 bits or 8 bits or?
That one is something that the community as a whole have done a pretty bad job of quantifying. I think you want as much resolution as you can get, but if that's 12 bits, I think that's probably okay.
Okay, it's just hard to know what's going to be our limiting factor. If we have something else that's the limiting factor, then we can go, well, 8 bits is fine because we're screwed over here anyway. That helps us potentially decrease costs or simplify things.
Sure. At what stage do you think we need to know that?
I don't think we need to know right now, especially it was a good point. I think we should do all of our testing on a photodiode first. I think that's a really good point. So I will get a big wide area photodiode from like, Hamamatsu or something. Maybe I'll just ask them for that as well.
Yeah,
And that'll simplify things.
I think that would be really helpful. I mean, Hamamatsu are usually pretty expensive for that sort of thing.
Fine. Yeah. Well, just because I'm getting the other stuff from them, I can ask them. But if not, I'll get it from someone else.
Yeah, it can't hurt to ask.
Cool. All right. Well, I'll make the BOM and try to fill out the
Great.
pieces that I would suggest, and then you can.
Yeah, ping a link in the forum or something, and
Cool.
I'll have a look and
I
make
also,
some suggestions.
like halfway through, I started recording this because I thought this would be a really good conversation for other people to see, especially the way that you drew it. Is that okay if I post that link?
Yeah, sure. That's fine. I mean, I can post a PDF of my scribblings on the forum, assuming I can upload files, or I can stick it in the wiki or something. I'm very happy to share it anyway.
Cool. I'll post a link to our discussion too, so people can walk through. Because I think it's actually really important to walk through the logic of the lens and everything. I'm assuming it's confusing to others, not just me. Maybe, but I don't know.
Yeah. I strongly suspect it will be.
Cool. All right.
It's one of those things that I keep telling people is totally obvious, and then realize I've been working full time on optics for many years. And,
right, you have a very unique intuition.
You get a slightly skewed perspective on what's obvious.
Cool. Okay, all right, I'll post that stuff, and then we'll go from there.
Awesome.
All right.
Right, well, have fun, and I'll keep in touch.
Sounds good. Talk to you soon.
Cool. Okay, see you later.
Bye.
Bye-bye.